Hello everyone, my name is Daniel Elabd, and today I will present my project on 3D printed graphite PDMS composites for soft stretchable sensors. Here's a brief overview of the content I will go through today. Firstly, I will go through a brief introduction as well as the motivation behind the project. I will then move on to the methods used and talk about the results achieved to date. Finally, I will briefly discuss the results and talk about the future work that needs to be done. So stretchable sensors are vital for both physiological monitoring and soft robotics. These have many applications such as wearable sensors for bioimpedance, ECG, temperature, and more. Other applications involve the use of pressure sensors on a robotic hand and sensors on snake-like robots which act as a sensing skin. There are a lot of different techniques to fabricate these stretchable sensors. Firstly, we have stencil printing. This requires a mask and physical contact of the sensors, and this therefore doesn't allow printing of closed surfaces. Screen printing is another technique, but this also requires a mask and contact. One other option to consider is inkjet printing, and this solves the issue of a mask and contact, but is unsuitable for high viscosity inks. Therefore, the most practical solution would be extrusion-based printing. This is contactless printing with the ability to operate with high viscosity inks. As we can see in the image, compressed air pushes the ink out of the nozzle at the set pressure. Therefore, the aim of this project is to use an elastomer, which is PDMS in this case, with conductive fillers such as carbon or silver as inks for printing sensors. These would be used for physiological monitoring and force sensing for wearables and surgical soft robots. Moving on to the first section of methods is the ink fabrication. This was done as follows. Both PDMS and graphite powder were mixed with heptane separately. Then, both mixtures were added together and appropriately mixed to give the final graphite PDMS ink. The amount of heptane controls the viscosity of the ink, and the ratios of PDMS to heptane and graphite to heptane were adjusted according to the extruding nozzle profile and the diameter being used. There are two profiles of the extruding nozzle, straight and tapered, as shown in the images. Tapered nozzles were used as less extruding pressure is needed with these, hence allowing for finer printing. The nozzle used had an inner diameter of 27 gauge, which is equal to 210 microns. An Elabd 2 3D bioprinter was used. Both the ink viscosity and print parameters were optimized for the 27 gauge nozzle. This resulted in the following parameters, with a minimum extruding pressure of approximately 6.5 psi, a print speed of 15 mm per second, and a layer height of 0.08 mm. This is the height at which the nozzle prints away from the substrate. All printed patterns were made on a flat layer of fully cured PDMS. The patterns were made using G-code scripts, and these were used as opposed to STL files from CAD design, as they allowed us to have finer and better control over the printing process. The patterns were printed, and they were all cured at 70 degrees for 2 hours. The images show the printed patterns. A rectangular spiral or an inductor pattern was printed at two different extruding pressures, 8.5 and 6.7 psi, to show the effect of the changes in the extruding pressure. A meander pattern and lines pattern were also printed for resolution assessment. In the G-code script, the minimum defined separation between two tracks was 0.7 millimeters, and we will see the measured separation in the results section in the next slide. The adhesion between the printed ink and the PDMS substrate was also tested, and strong adhesion was achieved after curing. The images show the prints under a microscope with measurements of track width W and track separation D. Several measurements for W and D were taken, and the average was calculated. The standard deviation is also shown. For the rectangular spiral, we can see the difference in track width as an effect of the change in extruding pressure. The higher pressure, 8.5 psi, results in a larger width of around 665 microns compared to that with 6.7 psi, with a track width of 315 microns. In the line sprint on the very right, the minimum achieved track separation D was approximately 234 microns. The width of tracks was slightly less than the previous print, as the extruding pressure was slightly less. We can see that a small pressure change of 0.2 psi resulted in an average decrease in track width equal to 87 microns. The minimum achieved resolution was around 234 microns for the track separation and 228 microns for the track width. Ideally, the goal would be to reach 100 microns for both of these. This is the commercial PCB resolution, and therefore it would be significant if this was achieved with our method. There is a lot of work to be done in future. Firstly, optimization for the 30 and 32 gauge nozzles needs to be done, and this will aid us in achieving the resolution goal of 100 microns. Moreover, in the prints, corners were not sharply defined as we can see in the image, and this means that the print path needs to be modified to achieve finer corner prints. This can be done by modifying the G-code. A very interesting approach will be attempted where printing occurs within uncured PDMS, that is embedded inside the PDMS, and this can allow for exciting multi-layer prints. Parameters such as viscosity and print parameters will also need to be optimized for silver PDMS inks. Eventually, all of these steps to take will be used in achieving the final goal of the project, which is to develop a stretchable, multi-parameter sensing system for wearables and soft robotics. And these would sense parameters such as temperature, ECG, force, and more. In conclusion, graphite PDMS prints were demonstrated for soft stretchable sensors, and with future work, a stretchable multi-parameter sensing system can be realized. Thank you for your attention, and are there any questions?